in our little calorie is 1/1000th of a food calorie. We're talking not large amounts of energy. All right, so we're going to do our exercise. We're going to go on. Basically, every single lab we're going to do, we're going to be doing this calculation, at least to some extent. Sometimes multiple times, but at least one part of every single heat lab, you're going to have to make this calculation. It's our calculation to find the heat. But to know that, we need to have the heat capacity. We have to know how much energy do I need to add to something to get it to change temperature. Now, specific heat capacity is one of those many constants that any material has. If you look up a material, there's lots of things associated with things like its density, its specific gravity, its melting point, its boiling point, its molecular mass, a lot of other things. One of those many constants is the specific heat. Now, specific heat, as I mentioned before, if you're a solid, liquid, or gas, it does change. It does change as you change phase, so it's not always the same. But our symbol is a lowercase c. Our unit, joule per kilogram degree C, or calorie per gram degree C. Notice when we use joules, masses have to be in kilograms. When we use calories, masses have to be in grams. It's the amount of energy to change that one mass, 1 degree Celsius, or 1 Kelvin. Remember, this is why we can use Celsius, because it's a change in temperature. Anyone need more time? Oh, I'm going to add this here. So, like for liquid water, notice I said liquid water, because if it was solid or gaseous, we'd have to do other things. C for liquid water is 4187 joules per kilogram degree Celsius. Or, it's also equal to 1 calorie per gram degree Celsius. So, depending on what we're doing. And you may not think, well, that doesn't sound very much, especially in calories, but let's keep in mind, like solid aluminum. Its value for C is about 900 joules per kilogram degree Celsius. Copper is about 380. So look at our aluminum. If I put the same amount of heat, if I had the same amount of heat to some aluminum and I had the same amount of heat to some water, the aluminum is going to go up almost 4 degrees in the same amount of time, with the same amount of energy that water will go up 1 degree. Yes, ma'am. 4,187 joules per kilogram degree Celsius. 4,187 joules per kilogram degree Celsius. Conversely, our aluminum is also going to cool down faster. When it loses about 5,000 joules of energy, it will have gone down about 5 degrees. Our water will have only gone down about 1 degree. This is why water takes an enormous amount of time to get warmer and to cool off. Other things, not so much. Now, although this is one of those properties of water that make water unique, liquid water has this very high heat capacity. Are there things with higher heat capacities? Yes, but you do not find them naturally occurring on the Earth. Things like hydrogen and helium both have higher heat capacities. But any helium or hydrogen they get in the atmosphere, because of their size, because of their mass, will immediately, their velocities are just in normal everyday temperatures, will give them a velocity that allows them to escape the Earth's gravity. So they basically go into orbit and go into space because of their very small masses on that. But it also means, anybody need more time? That water heats and cools more slowly than other materials. You know, especially our local weather is controlled a lot by the fact that the Central Valley heats and cools very rapidly, and the ocean doesn't. But if you went someplace like Lake Tahoe in the summertime, and you took the temperature of the lake, is the lake water going to change from morning to evening? Is that lake water going to change? No. But at 3 o'clock in the afternoon, you put your hand on a rock. What's that rock going to feel like? It's going to be hot. I mean, those granite rocks get darn hot. But a hot day, you can almost cook something on them. But you got that same rock at 3 in the morning, 3 a.m. It's going to feel cold. Very large temperature difference between day and night on that. Even the ocean takes months to heat up and cool down. This is one of those factors that keeps the Earth fairly well regulated on temperature. There's not a lot of heating and cooling between summer and winter. Most of the heating and cooling takes decades. Decades. That's why we just finished recently, within the last year, we finished at the high point of the Pacific Decadal Rhythm. This is one of the reasons why the poles have been, melting more, and they also freeze very quickly, though, because it's the end of the decadal rhythm. Also, in fact, we've just finished a high solar cycle. The solar output has actually gone down within the last few years, which is why temperatures worldwide have started going down. Regardless of the fact that most of all this global warming data was, they admitted that it was all made up. So, what the heck? Okay, anthropomorphic global warming. In other words, human-caused global warming. The Earth heats, it cools. That's a natural cycle on that. It's like carbon dioxide. Carbon dioxide actually went up a little bit. It'd actually be better for everybody. Plants grow a lot better when there's more carbon dioxide. Food output actually increases as carbon dioxide goes up. It's one of those things. Can be your friend. All right. So this is one of those things. But how are we going to calculate it? In our next lab, we actually have to calculate it out. To find the temperature, there's 3 factors to find that heat. Mass, how much mass? Obviously, how much is there? I had 10 joules. Do I have 1 gram? Do I have 1,000 grams? What's the specific heat capacity? How much energy does it take to change? And how much change in temperature? It's going to depend on that energy. And so we put these together, we get a formula. Heat equals mass times specific heat times the change in temperature on that. It's a C. And keep in mind, delta T is always final minus start. Final temperature minus the start temperature. Which means, could heat be negative? Yeah. That means you're losing energy. Energy is not a vector, but positive energy means you're gaining it. The object's gaining energy. Negative energy means it's losing energy, which becomes very important when we talk about conservation issues, which is calorimetry, which we are going to be doing in your next lab, because some things gain as some things lose. But the sum has to be 0 on that. Anyone need more time? So, just a sample here, and we're going to do some more next time. But how much energy is required to raise the temperature of 15 grams of water with a specific heat of 1 calorie per gram degree C from 5 degrees to 25 degrees? Now, there will really be labs we only do this once. There's sometimes you have to do it multiple times within just one equation. So, here, though, mass. What's the mass of our material? 15 grams. Units are very important. Specific heat. 1 calorie per gram degrees Celsius. And we look at these two. Grams, grams. They match. If they're one's kilograms, one's grams, we have to change one of them. T at the start, our start temperature, 5 degrees Celsius. Our final temperature, 25 degrees Celsius. Q equals MC delta T. Everyone with me so far? Where I've gotten my numbers and things like that. Jonathan? We best not be texting. You okay? So, 15 grams times 1 calorie per gram degrees C. 25 minus 5 degrees Celsius. So if we look at this, grams cancel grams, C cancel C, leaves me with calories. Remember, specific heat capacity is a proportionality constant. It's what allows us to equate mass and temperature to energy on that. So I get 15 times 1 times 20 calories, or 300 calories. Questions? Anyone need a little more time? Remember, this is calculation appears in almost, it will, and then we'll be done. And that's not that, and not that, that. Calorimetry, because that's what your lab is about next time. Calorimetry. Process to find the energy in an object. It works by conservation of energy. This is like, how do they know that that candy bar has 135 calories? Those food calories. Well, they do this process called calorimetry. Basically, a lot of times they burn it. But calorimetry works by conservation of energy. That there is no net change in energy. Yes, ma'am. We're going to do something. I don't know if we're going to do chocolate chips. They didn't burn very well last year. They were hard to burn, so I might find something else. Marshmallows don't burn very well either. Chips burn really well.
I burn marshmallows like every year. They burn perfectly fine. Don't eat it.
All right. So there's no net charge. Shh. No net change in the energy. Conservation energy. All objects are taken to thermal equilibrium. That's the thing about calorimetry. The final temperature of all your objects, basically each object is going to have an MC delta T term, but the final temperature is always the same for everything. Shh. Which means something is going to gain, something is going to lose, but the sum of them will be 0. And this could be many objects. We're going to do it with 2, but it could be 3 or 4 or 5 objects. It depends on what you're using for your system. In other words, we have an MC delta T here plus an MC delta T there. They're going to equal 0, which means 1 is a positive and 1 is going to end up being a negative. This is where making sure that it's always the final minus the start temperature becomes very important. Not just the high minus the low, because it's the final. Because some things are gaining, some things are losing. But the sum has to be 0. Conservation of energy. That's what it's all about, conservation of energy. All right, so next time we do lab, proper clothing, closed-toed shoes, long pants, long skirts. Grab your bags, bring them back to your desk before you start putting things in, and then put all the chairs on the tables, please.